All right, thanks everyone for joining us today. We're very excited to have some of your time to present some of our group's work on next generation technologies. We'll be talking throughout about mainly wearable technologies in a couple different domains and how our groups are innovating in those domains to improve the tech and deploy it out of the lab and into other challenging environments. I'll be joined by my friend, Dr. Jonathan Reeder today. My name is Dr. Patrick Ganzer. Background is in neurotechnology and neuroscience. I'll be focusing on next generation neurotechnology, mainly talking about wearable interfaces. Here's how the brain-computer interface works. So the first component is an implant that's surgically placed in the area of the brain that lights up when you think of movement. So if you want to open or close your hand, this area becomes active. Although this piece of technology is very effective and mediates a lot of innovation in the neurotech space and brain-computer interface function, there are some shortcomings. No technology is perfect, so we'll be talking later in the slides about improving that component of the technology. Once we record brain activity, we then decode it. And so we can really see what patterns are related to what kind of thoughts related to movement. And after that, we have to do something in order to make the movement happen. So you see that in the schematic and in the video at the bottom left. This is a wearable interface, consists of hundreds of electrodes, which allows us to stimulate different muscles on the forearm and make the hand move in the desired way. I'll show you a video to the right here of the interface in action, where the participant is thinking of a movement, shows up in the top right. That then triggers stimulation on the forearm to make the hand move. And then they can carry out different object manipulations, either large objects or even small objects, like you see here, the red stir bar. So this is how the interface works, and I'll be talking about how we're working to improve different modules, starting with the muscle stimulation system. So as you can see, the muscle stimulation system is not exactly perfect. This is a research grade device. It has to be put on by another technician. The interface isn't necessarily aesthetically pleasing. It could potentially be wireless. And furthermore, the electronics that power this interface are quite bulky. So if we think about wanting to get this type of system out of the lab and into different environments to be tested on different patients, there's definitely some room to improve. So you see here the general size of the interface. It can fit on really a large size dinner table. These are the power electronics, the control electronics for different channelization to target different muscles. And what we've done over the last several years is moved from field programmable gate array control to more microcontroller based interfacing to shrink the electronics down by really over an order of magnitude, which is really exciting. So this is now potentially portable. It's about the size of a VHS tape there, the white box. And furthermore, beyond miniaturization to get this system out of the home and into or out of the lab and into other environments, we also have improved the sleeve fabric. So the electronics are now embedded in a sleeve that can zip up around the arm. Here you see to the right, the interface on a participant where it zips up and now can be wheelchair mountable or put on a belt buckle and potentially tested in different environments to improve the quality of life of patients using this. So some of the most recent work that we've been doing is now getting this out of the lab and into the home to really see how it functions, to learn if our engineering goals are achieving user needs, and see if we can actually improve the quality of life in a more challenging environment. So one main change we've made is instead of brain control over the stimulation on the forearm, we're moving to tablet-based control. So there's pre-programmed grips that the user can select for different objects, whether they want to grab something small or even large. Here you see the participant grabbing a coffee mug and the tablet control display to his left. And excitingly, we've also been deploying this interface in a very challenging environment course, under supervision in the participant's home, which is very exciting. So he's been working on this tech for almost a decade, and he can now use the system, which is wheelchair mountable. You could see the electronics on the back of his wheelchair, and use tablet control to do activities of daily living that he really cannot do without the system. So this is very exciting. We're learning a lot about the systems. So in closing, on my neurotechnology section, the last thing I'll talk about is potential improvements to the brain interface itself. As we highlighted in the first couple slides, the brain implant component is not perfect, although it does mediate a lot of cool functional improvements and also advances our understanding of the human brain. Things can always get better. So this is invasive. So it's in order to be placed, it requires open brain surgery. Maybe we can mitigate that surgical risk by using a different interface or a different interface approach. Furthermore, the implant consists of a hard metallic interface, many electrodes, which has a modulus mismatch with the much softer brain. So this can lead to micromotion of the interface, and over time, um, aggravation of the tissue, scarring of the tissue, and maybe even failure of the device, which are all big problems. So one of our approaches to improving this, and something that we're working on at Battelle, as well as with collaborators at the University of Miami, CNMI, and the University of Indiana, is funded by a government program, and it's called Next Generation Non-Surgical Neurotechnology in the top right. What you see in the schematic is our approach to mitigate both surgical risk potentially, as well as use miniaturization to improve neural interfacing. We call the system brainstorms. Stands for brain system to transmit or receive magnetoelectric signals. And bubble one is where we get the non-surgical component. So we use magnetoelectric nanoparticles, which are very small, about 20 to 50 nanometers wide, and we can inject them into the circulatory system. Once they're in the system, we can use a magnetic field over the head to pull them from the blood into the brain tissue to allow for neural interfacing. To the right, you see a two-dimensional representation of the magnetoelectric nanotransducer. It consists of a magnetic core in green and a piezoelectric shell, and these two components are lattice matched. If we want to stimulate neural tissue, we can use a magnetic field from outside of the head, modulate these particles, there's millions of them in the tissue. When the green core becomes magnetized, it will induce a strain on the piezoelectric shell that will then mediate the generation of an electrical field for stimulating tissue. And if you want to record from these particles, you generally use the opposite ordered approach, where the electrical field of neurons will couple to these particles and then change the ability to magnetize them. So this might be a new, novel, next generation way to interface with the brain or other nervous tissue without requiring surgery, again, leveraging nanotechnology and miniaturization.